Hi, everybody. I'd like to welcome you to the last session of the day. This is the methods and applications of modeling and simulation validation. I'm Benjamin Ashwell. I'm the head of OED's Sustainment Analysis Group, and I'll be chairing this session. For our first speaker, I'd like to introduce Dr. Anna Capp, who'll be talking about model verification in a digital engineering environment. She's a researcher here in the Operational Evaluation Division of OED.
Thank you, Benjamin. Let's hope I can drive this clicker well enough. First, I want to thank the DataWorks organizing team for letting me present some ideas today. So what I'm going to talk about today really is how we do model verification in a digital engineering environment. And I'd like this to be a conversation about maybe shifting the framework for what verification and validation mean as is typically practiced for DoD acquisition systems. But again, this is a framework. I'd love to hear your thoughts afterwards. So what is digital engineering? Because there's about 20 to 30 different definitions, as far as I can tell, out there on the internet. So I want to frame the discussion first as what I'm using digital engineering as the construction of digital models representing all of the characteristics of a complex system under development. When I say all of the characteristics, what I mean is architectural models, data flow models, performance models, and simulations. So really, digital engineering takes advantage of that design using those digital architecture models, and it's an integration of multiple layers of models across the system. And really, the intention is for these digital twins, dare I use that word, to support the model through system production and sustainment. Now, with the digital engineering environments, we can use advanced computational resources to really model the end-to-end operation of weapon systems. And what I mean here is the weapon system as it will be used in a threat-contested environment. Now, what should that model verification and validation activity look like then if we're looking at the end-to-end operational mission and representing that in a digital simulation? Really, we want those verification and validation activities to be the same as if it weren't in a simple or weren't in a digital environment. And really, it should be scoped. Our activities should be scoped to the end-to-end mission and to the availability of real-world data. Our verification, importantly, should inform that validation plan, that collection of live data to validate the model. And the verification should accurately characterize what we know about the model, what we know we don't know about the model, and what we think our error in the model outputs are. Now, as these digital environments become more and more complex, we start looking not only at single models or simulations, but at what I'm going to call federated models. Now, these federated models are, can I use this as a pointer somehow? I'm sorry, probably not. So these federated models really are a system of individual models that feed into each other, maybe not necessarily in a series way, but maybe in a branching way or in a parallel way. Here I've represented a simple end-to-end model where we have the blue system under development and then the red threat-based model that we fly in a simulated environment, our blue system under development against, with the model output over there in purple being what ultimately we're interested in, that being the operational response, the mission response for that system under test. Now, when we look at these federated models, they have to combine data from multiple sources. We have very limited capability to collect live data on threat actions. In fact, our threat action data is limited by our knowledge about the adversary shot doctrine, our ability to create emulators of the threat, hence our knowledge of adversary threat performance, and our ability to rapidly deploy and field emulators in response to a changing threat environment. And so when we look at validating these federated models, we have to consider that these are not necessarily just digital models, but they're models that come from a multitude of simulators. So we could have surrogate testing. We could have engineering emulators. We could have some live data feeding into here. And then particularly on the red side, we're going to have models that were built based on SME judgment. And so when we look at this entire federated model system, how do we allocate resources for validation of these complex models? We can't afford in the DoD acquisition cycle to do live validation of every component of this model. And in many cases, when we're talking about a true end-to-end blue versus red simulator, we also can't afford to do validation of the model output, to do operational validation of the model output in many cases. And so we need to have a framework or a way that we assess which parts of the model matter for the operational assessment. Maybe some of these lower level models aren't really important because the way the data gets transferred up the federated model chain, if there are large errors in here, they eventually get dropped in the model. Or maybe that's a really important piece of the model and we need to focus resources on it. How do we determine that a priori? And how do we define when we're allocating operational or live test resources to federated model V&V? How do we define our accreditation criteria? How do we define what live data we're going to collect for validation? And when it's good enough to do validation, say by registration, by comparing one model against a legacy model and seeing if they perform similarly. And really, that's the problem that I'm going to be talking about today. And I'll be honest, I don't have a solution. This is a thought piece. It's probably the least technical talk you're going to see today, but I'd like it to open up a conversation. And so here I want to describe a notional missile system as what we're going to be using for the rest of the talk. And here we have a blue missile, and this missile, it's going to have multiple payloads. It's going to be a short-range ballistic missile, but it's going to have a seeker on it, and it's going to fly against an anti-ballistic missile threat, for example. And so when we start to look at that, we ask what portions of this model can I realistically accredit with live data? What portions are going to be a SME validation only? And what portions are maybe validated through model registration, through either comparing our new models to existing legacy models, or to developing two independent models and seeing how they perform against each other. So that's the problem. Oops. Now, one of the things that I'm going to say, though, is I'm not saying that we should get rid of V&V with this. The traditional V&V process should be applied to these complex models. However, I'm going to argue that oftentimes when we talk about model V&V, we have an accreditation plan, then we have a verification and validation plan, and a verification and validation report, and then an accreditation report for those models in the OT community. I'd like to suggest that if we break up that verification and validation process, we can leverage and do a smarter verification from an operational test perspective that can leverage more information about the model at the verification step to allow better informing of our validation plans. Now, I keep wanting to use these buttons up here. Now, before I get any further, I've noticed in the community that we have lots of different definitions sometimes of verification and validation, depending on if you're talking to an engineer, a tester, or a statistician. So here I want to focus on the definitions that I'll use for the remainder of this talk. So verification, I think we can pretty much agree, is the process of determining whether a model has been implemented accurately according to the conceptual description of the model. And that's where you get your unit testing and do your outputs match your inputs. But then I'd also like to extend that definition and have us consider whether verification should also include determining what the model variance is in reference to its intended operational use space. And I'll talk about that in a minute. And then finally, validation can be a hot button issue too. Here, I'm using more of a statistical validation term, where we compare model outputs systematically and rigorously against real-world data when possible. So now if we go back to the accreditation V&V chart, I've highlighted some questions here, and in bold are the questions that I think is most important from an operational perspective. So when we start to think about the conceptual idea of a federated model, a model of models, one of the things that I, as an operational tester, want answered is, how is this model going to be used? It's a lot different to accredit a model that will be used in developmental tests or even operational tests compared to a model that will be used in operational mission planning in the field. And so once we know how it can be used, we can then say, what is its operational space? What are the factors and responses? What are the variables in its operational environment? And then I'd like to add a step to our model verification where we characterize that model space. We understand how the model responds across the operational space. And I'll talk about that in a minute. And then finally, we need to think about our different levels of validation, where the gold standard is going to be live validation. But again, especially when we're talking about end-to-end V&V against a threat, we don't have the possibility for live validation. So how do we expend those resources? And can we accept different levels of validation? Live validation, SME validation, validation by registration, for example. And then finally, when we're talking about accreditation, I think one of the important things also is, for these digital engineering environments, is understanding if there's going to be a support plan in place for that model through the life of the system. Digital engineering enables sustainment of the system and keep custody of all system performance data throughout the life of the system. And so I think we also need to consider support plans within the VV&A process. Now, for my notional missile system example, I'd like to explain this model response for this notional system, because this is what we're going to be using moving forward. So here we have our missile, and we're looking at two factors. We're going to be looking at how fast the missile flies in its terminal region on the y-axis, and then the threat, the anti-ballistic missile, time to engage on the x-axis. And here in this notional system, maybe the probability of kill for our system, the ability of our system to do damage to a target, is going to be large when that missile is flying fast and there's a low time for the threat to engage. But then maybe it's going to be low when the missile is flying fast, maybe not as maneuverable, but there's a large time for the threat to engage. This is the operational space of the model response. Now that I've framed the question, I want to go back to this slide very quickly. And knowing that operational space, in this notional example, we can think, well, maybe that looks pretty complicated. That's not a generalized linear model, which is usually what we fit data to in the OT realm for model verification and validation. So maybe this V&V process should be iterative instead of a one and done verification, validation plan, and then verification, validation report. So now when we think about model verification and validation, I've thrown up here a modified fishbone diagram that shows our model response. I think most operational testers here would be familiar with something like this, where we have the model response and then we have our testable factors. This is something that we typically see in live testing when we're defining the live data that we're going to validate a model. But equally important in our model, in our federated model validation, is going to be these additional factors. These factors that we're not going to control, and we need to enumerate these what we may call logged factors, for example. The factors that we're not going to control in our live test because we can't. If anyone has a really good way to control dust and debris during live tests, let me know because I don't. And then also, we also need to enumerate what our known, unmodeled, and untested factors are in order to get a complete picture of what the validation of our model is going to look like. So are y'all with me so far? Okay. So now, like I said, this isn't going to be a technical talk, but once we have our model factor space, we can then look at our test designs. We can then look at, well, I need to characterize that operational space of that model. This is a very complex model. Now, my colleague, Curtis, is going to talk right after me about ways that you can do this. So I'm not going to steal his thunder, okay? But I'm just going to say that for when we can't assume in federated models a generalized linear model a priori, we may want to shift away from optimal designs for model validation. But the goal of this is not to design live test points for this model. The goal of this is to understand how the model performs. So we need to have enough runs for our model verification to understand the contours of the model response space. Because if we understand the contours of model response space, we can then make a better, more informed judgment of what our model validation using live data can be, if possible. Does that make sense? So we're going to want to really figure out what the shape of this model response looks like. And it's pretty easy in a two-dimensional factor space. It's less easy when you start to get a 12-dimensional factor space. And so that's what I'd rely on my statistical friends to help me out there. But characterizing this to build a meta model, a statistical model that describes that response space, is going to be key. Now, once we've described the model response space, then we're going to want to describe the errors in the model response space. And I've got 3 ideas up here. Like I said, Curtis, he's going to give you a much better explanation of how you do this. But the key is we want to know not only how does the model respond operationally, the end-to-end model, but we want to also know when we change the input parameters for each step of that federated model, how does it affect the output? And what is the variance? What are the range of model outputs in that federated model? Now, if we get those 2 things for a federated model in the verification step, if we can understand how the model responds from an operational perspective, what my p-kill is when I change these factors in the model out for the model output, and we can understand what the errors in the model are, then we can focus on validation and we can make a more informed decision on what model validation could look like for a system. So we characterize model response space by identifying key operational factors, not input parameters to a model, but operational factors that could change the response the most. We could identify the contours, the regions of the operational space that are changing the most. And then we can do better, have a more informed validation strategy. Now, if we get that, we can then take the federated model and we can allocate and prioritize our limited test resources, both our computational resources and our live test resources, to portions of the model that matter the most. So here I've taken that blue versus red model and I've changed the color coding here. Again, notional example, where I've said, well, maybe based on that mapping of operational space that we did and that sensitivity analysis, maybe we know that on the blue side, getting a model for that missile is really important, or getting live data to validate that missile performance is important. I maybe don't care so much about that sixth-off, that specific validating that specific sixth-off for missile flight or the specific payload release mechanism, but I care about collecting live data on how that missile performs overall. Maybe we say, well, we also need to know what that missile seeker does, but we're not going to fly that missile against an ABM threat. So maybe we need to reprioritize that. Instead of looking at live testing data, we're going to validate it via surrogate testing. Maybe we have a threat emulator, or maybe we can take advantage of some other DoD systems under test and get similar data and validate it. But really, once we understand that operational space, we can do, or that model space, we can do that prioritization for the operational mission. And that's all I have. I mean, really my point is I'd like us to consider decoupling model verification from validation to make it a true stepwise process, so that our model verification from an operational perspective can better inform our model validation strategy, including allocation of test resources for highly complicated models, these federated models. That's all. So I see there's some questions.
So can everyone hear me? Looks like yes. So we have a question from Zoom land that I saw also as well. Question from Chris Henry. The operational accreditation process was intended to determine the acceptability of the uncertainty of the output of the model, the perturbation of model uncertainties through the federate of models, as it relates to the intended use of the M&S. I believe that you are getting at different means to determine model uncertainty. Is that correct?
So model uncertainty is one of the key aspects of it, yes, but also identifying not only the model uncertainty, but the key operational factors that we need to both run the model against and run the live testing for. Because often if we focus just on model input-output uncertainty, then we're missing that operational perspective.
Scott Schutzmeister, also with IDA. You highlighted the digital engineer environment. Mm-hmm. Are you saying that pre-digital engineering, this was an issue, and now that we are tackling, however we want to talk about digital transformation, there's an opportunity? Can you kind of go more into what was it like before and where that digital engineer piece is making this an opportunity?
No, so thank you for that. So I think really we've seen a change in the complexity of our models over the last 20 years or so, really. And particularly as we are doing true battle space end-to-end scenario modeling, we have to shift to different approaches for validating those federated models. The digital engineering environment is, in my opinion, going to allow us to have better custody of the data from those models and how that data fits in with requirements and engineering designs. But to be honest, digital engineering in DoD is so new that that's a hope at this point.
Thank you. Other questions? We have a couple more minutes till the next talk, so if nobody has an eye.
Y'all are an easy audience.
Thanks, Joanna, for the talk. Can you give a bit more context for how the space-filling models play into when you're looking at a federated model and trying to understand what data points that you want to sample? Because the portion that I was confused about was when you're developing like an n-dimensional space-filling model, is that for every box of your federated flowchart?
No, so that's a really good point. So I think it depends on the system under test and the model under test. For a model that has 24 components, like the one that I showed up here, I don't necessarily know that it's an appropriate allocation of resources to do a space filling model with the Monte Carlo error analysis for all 24 components. And more than that, you don't get a gestalt view of the entire system performance. So in this case, I was talking about the final model output. And assuming that the model allows you to input operational parameters, which I would hope it is, especially if it's going to be deployed, then really what I'm talking about is building a space-filling model for that model, final federated model output based on operational parameters, or surrogates for operational parameters, depending on how the models are coded.
Okay, thank you.
Yeah.
You can ask your question now.
Anybody else? Okay. The last one, and then we'll go to the next speaker.
Thank you. Yeah, Kyle Colsty from the Scientific Test and Analysis Techniques Center of Excellence, and I'd like to offer up, our team has been working for a while on a concept called model validation levels, which I hope might be able to address some of the issues you're curious about. And instead of explaining it all, there's a talk in room D in a couple minutes by Kyle Provost on model validation levels. And it might address some of the things about where to allocate resources, the quality of the authority of the referent that you're using in the validation, and some other aspects. So I'll just throw that out there as something if you'd like to talk about later. Thanks.
Perfect, thank you.
Okay, with that, let's thank the speaker again.